Now let's focus on some security like IP security or IPsec. The security architecture for IP is for this IP security. It is an open standard. It's defined in an RFC, the request for change, in 2401. IPsec's been around for a little bit. It has a suite of security services, and it has many protocols involved with it when it comes to IPsec. It does operate at layer 3 of the OSI model. So remember, layer 3, that's our network layer. That's where we're talking about IP. That's where our routers are. That's where routing takes place, logical addressing. IPsec works there as well. Now, it does provide security for layer 3 and up above. So the data's coming up, it hits the IPsec, so everything above it should be protected. That's what it's supposed to be applying security for. Now, the three components of IPsec, major components, I guess I need to say, is the modes and the protocols and the Internet Key Exchange, the IKE. Now, the modes and the protocols are really going to focus on because we have transport mode and tunnel mode, and we have ESP and AH. And we're going to look at these a little closer. But those are some of the components of IPsec. And there are a few more, but these are the ones that I really want to focus on that I think are going to be important. Now, here is the IPsec architecture of how it kind of behaves. And you can see we have transport mode and tunnel mode up there at the top. And depending on if we use the AH protocol or the ESP protocol, depends on the type of algorithms that we're going to use. So AH, the authentication header, is going to use that authentication algorithm and then go down to the key management. But you can see over on the right-hand side, we have the ESP protocol, and it can do authentication algorithms and encryption algorithms. And then we always end up down at the same place. But you can see here from this architecture that AH is concerned with the authentication algorithms, MD5, SHA, the hashes. The ESP is not only concerned with authentication, but now encryption, like triple DES, DES, and AES. So let's look at these two things here real quick, AH and ESP that I keep mentioning. The authentication header, all right, IP protocol number 51, might want to file that one away. Might not be super important for this exam. This thing, the authentication header, provides authentication and it helps in anti-replay services. So the authentication of our information is taken care of by AH. The thing that we do need to know about this authentication header, it does not encrypt the IP packet payload. All right, just the header information, not the packet payload. Now, ESP, on the other hand, that's our encapsulating security payload. Protocol 50 provides authentication now, and it can help in anti-replay services, and we have packet payload encryption now. So instead of just the ends being encrypted or taken care of like for authentication headers, ESP will take care of the whole thing. Now, ESP can be used standalone, or we could use it in conjunction with our authentication headers as well. So it's going to depend on your needs, right? There's no one better way than the other because you may be employing some other technologies in there as well. So I can't tell you which one you have to use or anything like that, but it depends on your organization. What we need to know is what these two things do. And then we talked about those modes, right? I mentioned the modes, the tunneling mode and the transport mode. Now the transport mode authenticates and encrypts only the data payload. The original IP header remains intact. So if you have that networking background, you know that if the header remains intact and we start traversing over networks and start going through the internet, everybody can see that header information. They have to. Routers route by that header information. So we don't necessarily have a tunnel situation there, right? We have encryption of the data payload, right? So the data is good, but the endpoint protection is not really there. We don't have a tunneling situation here. Now, tunnel mode, on the other hand, it authenticates and encrypts the entire IP packet. This actually adds in a new header. So having that new header, now we have a tunneling situation, a tunnel, if you will. Because, think about tunneling for a second. If we have a tunnel, right, everybody sees the tunnel on the internet. Well, in order for that tunnel to work, we have to have header information on there as well. Source and destination and tunnel configuration information. It has an IP address on its own, right, on the tunnel. But we also have the original data on the inside that also has header information, destination and source, and packet information inside there. But the tunnel is hiding this. That's its purpose. So we can have a tunnel, say from router to router, or whatever devices, network devices you have, layer 3 switch, you could have tunnels out there, and that data should be protected from end to end. And when you go from another router to another router, that should be encrypted as well, as long as you have the configuration right. So know about those two modes. Transport mode, which takes care of the payload. I think I misspoke earlier when I said it encrypts the header information. Not the header information, just the payload information. And then tunnel is the entire IP packet. So here's our authentication and encryption algorithms that you need to be familiar with. Those authentications, right? We have the MD5 and SHA-1. For our key exchange, we have the DH. What's that stand for? You remember? The Diffie-Hellman, right? And then the payload encryption, we can use DES, triple DES, or AES. AES being the best out of those, obviously. Now, what about data communications? Earlier, we talked about voice, and I mentioned analog, but I didn't really mention digital. You know, analog works off those frequencies, the tones, the radio frequencies of how it's passing information from one side to another. Digital, on the other hand, is, to me, a little more simplistic. It's either all or nothing. It's highs or lows, or ons and offs, you may hear it, or ones and zeros, right? If it's on, it's one. If it's off, it's zero. It's nothing. So that's the digital world, right? They say that, well, that's computers. That's how they talk. And that's absolutely true. They're binary creatures, and they understand yes and no. That's probably the most simplistic programming you can get. But we can make it extremely complicated, right? So it's either yes or no, on and off. That's the digital world. Now, we have something called secure shell. And I mentioned that earlier, that this is what you should use to take place for Telnet. But secure shell can do a lot more. It includes remote logon, like we talked about for Telnet. We can use it for file transfers. So we can actually take secure shell and stick it on FTP to make it secure. We can also have command execution through secure shell, or SSH. It supports port forwarding, and that redirects other protocols through an encrypted SSH tunnel, giving it, like FTP, that protection, that sense of security that we want when we're using that protocol. Now, SSL and TLS, they've been around for a minute. You can have a VPN, an SSL VPN. Again, SSL, secure socket layer, or we can use TLS. TLS is the better of the two, the more secure. This works at the transport layer security, TLS. Now, 1.2 and 3, they are compatible. Now, SSL is a session encryption tool. That was developed by the Netscape folks. And if you've been in IT for a while, you probably remember the Netscape browser. Same folks, all right? They developed that a while back. And TLS now, though, is the open standard by the IETF folks, and it's an open standard version of actually SSL. It was built from SSL, and they made it better, right? Again, we're always trying to evolve, get better, faster, stronger. So TLS is evolved from SSL. Now, what about that virtualization? I mentioned that earlier. We can have virtualized networks. We can have virtualized desktops. We talked earlier about virtual applications. We can have virtual computers. So virtualization, what that does is adds a software layer between an operating system and the underlying computer hardware. That's one way of looking at virtualization. So I could have, say, a Windows 7 machine and run some type of virtualization software on top of that operating system that helps it communicate with the hardware. So we can have multiple guest operating systems running simultaneously on one physical host computer. I use virtualization all the time. I've got a pretty beefed up laptop. It's got 16 gigs of RAM and a pretty good processor in there. So I can run 3 or 4 VMs, virtual machines, or these guest machines at any given time. I can put, say, Server 2012 on there from Microsoft. I can put an Ubuntu flavor on there, version, guest operating system on there. I can put Red Hat on there, right? I have a copy of Red Hat that I can move from system to system. I can put other operating systems on there if I wanted to. I can put a Windows 7 or an XP if I wanted to play with that, or if I'm looking for vulnerabilities. And that's usually what I use these for, is like a lab environment. I can put a server operating system, I could put a Linux operating system, I could run Apache on this Linux, I could run IIS on this Windows version, and then what I can do is, say, demonstrate vulnerabilities in web services. I can say, well, this is what happens to Apache, this is what happens to IIS, this is what happens to an Oracle database, this is what happens to an SQL database, this is what could happen to a MySQL database. So I could have different VMs running different things, and then I usually have, an attacking VM that's doing the vulnerability checks or the penetration testing. And I can use those, like I said, in demonstrations. Like if I'm giving a talk somewhere, I can say, well, let's check this out. And I can show them on the different screens, right? I can bring up a VM, a guest operating machine system, and they can see what's happening and what's going on. You can also use this in your everyday life if you wanted to. Linux, we talked about the virtual desktops. Linux has had virtual desktops built in for a long time. You can actually have like 2, 3, 4 different desktops at any given time. You can just click down there on the bottom. That's where mine is anyway. Click on it and I get desktop 1. I click on it again, I get desktop 2 that could look completely different, right? I can do that with virtual machines. I used to have a job, a while back, that whenever I taught a different class, I had a VM for that particular class. So if I was going to go teach, say, a Security Plus class, I would have a VM set up just for Security Plus, right? I had all my tools loaded on there, all my presentation information was loaded on there, any like study questions, flashcards, things like that, just for that particular class. And then if I was going to go teach a Microsoft class, I would have a VM just for that. Now, it started to get a little out of hand for me. So what I started doing was then I started consolidating them, because I had one, say, for every type of security class, like CISSP, Certified Ethical Hacking, SANS classes, CompTIA classes, Microsoft classes, because they do have stuff on security now. I'd have a VM for all that. So I was starting to have like 3 dozen VMs, and that got a little unwieldy for me. So I started combining those. But anyway, not about me. This is what I'm talking about when it comes to virtualization. We can have multiple guest operating systems. They are also, what's cool about them, which I think is cool about them, is they're stored on a single file. So you can take that file, right? I could take it off my laptop and put it on my desktop that I have at my house. So I can copy that file over, and I can use that VM on that desktop now. Now you have to be careful when you're doing this on the applications you have installed, on the operating systems you have installed, because you don't want to violate any licensing agreements. So you can't create a VM and then give it out to all your buddies. All right, that's not legal, right? You're breaking the terms of service when it comes to licensing, because if you create a VM, a virtual machine or a guest machine, you're loading an operating system on there. That takes a license. If you load any applications on there that you've purchased, that requires a license. So if you take that VM and you start sharing it with all your buddies or coworkers, they're not really supposed to be using that, okay? So be careful with that kind of thing. You got to make sure you're staying within your licensing. Now, let's dive in a little deeper with that virtualization, because we talked about the guest operating systems, but we have a host operating system, right? Say the laptop that I'm actually storing or installing these guest operating systems on. But there's got to be something in between there. We talked about that software, and that software is the hypervisor. All right, so the key to virtualization security is the hypervisor. It controls access between the virtual guests, the guest operating systems we're installing, and our host hardware. Now we have two different types of hypervisors. The one I was talking about just a second ago on my laptop, because I have a guest operating system on there, is a type 2 hypervisor. So what happens is it runs as an application on a normal operating system, like Windows 7 or 8 or whatever you use, Linux, right? So you have your operating system that you use daily, right? You use it to, check your email, you use it to surf. It's your computer, the installation that you're used to. But you can go get software programs like VMware's virtual player. You can get VMware itself. You can get VirtualBox. You can use Microsoft's Hyper-V technology, right? It's virtual PC. I think that one's still around. You can take these applications and install them just like any other application on top of your computer, on your hosts. And then you open up that application and you can start creating these guest VMs in there. And those are your guests that are going to be using resources. But these guests talk to the layer 2 or type 2, hypervisor that actually talks to your operating system that talks to the hardware. But what if we had a bare metal server? Let's say we come upon a server, we buy one from wherever you get your equipment. We've got a server, it's got 128 gigs of RAM. It's got, 20 terabytes of storage. It's a pretty beefy computer, right? 4 quad-core processors. We're ready to go. We're ready to really crank something out here. Well, loading an operating system on a server like that, unless you're going to do something like database, is going to be a little bit of overkill. But you could think of the possibilities of how many virtual machines, how many guest operating machines do you think you could run on something like that? Because you got to think about your resource allocation. Every operating system takes some RAM. What applications you're going to load on that VM takes some RAM. So it just depends on the purpose of what you're going to use it for. But I'd say allocating 8 gigs of RAM to any server level system, maybe except for databases, should be okay. And it doesn't even have to be servers. What if you had a bunch of desktops out there or whatever you wanted to load on there? But this is a different type of hypervisor now. And this is what I was alluding to. This is a type 1 hypervisor. This guy sits right on top of the hardware. This hypervisor talks directly to the hardware. There's no underlying operating system. Some say that's better, and they're probably right, because now we don't have to worry about the underlying operating system. The only thing we have to worry about is the hypervisor. Because on a type 2, we have to take care of the host operating system. So if it's not patched, if it's not updated, if it's not secure, everything that's running on top of it inherently is insecure now. Because I could compromise the lowest level, and everything above it, like our hypervisor and all of our guest VMs, could be compromised now. Don't have to worry about that with a type 1. The only security we worry about with a type 1 is the actual hypervisor and maybe physical security. Now, talking about security, when it comes to all these guest operating systems, we have to secure them just like we do any operating system. You have to treat them like it's a quote-unquote real or physical computer. You have to update it. You have to harden it. You have to turn off those services. You have to patch it, right? You have to take care of it just like it was a desktop on your on your desk or a laptop or whatever type of computer you're taking care of. Now, there are exploits for these hypervisors that we need to be aware of. We can have exploits between the hypervisors because what the hypervisor can do for us, instead of just talking to the hardware, it can also share resources between, say, the host and the guest operating systems. I can turn on what's called a shared folder, and I can actually copy information from my guest operating system down to my host. Or I can go from guest to guest. So I can use cut and paste, those shared drives, shared network connections. So again, where there's a vulnerability somewhere that could take advantage of our other guest operating systems. They could also exploit the hypervisor and jump out of the hypervisor. So let's say they are in guest operating system number 1. If they compromise the hypervisor, they may be able to get over to guest operating system number 2 that does not belong to them. Virtualization is huge when it comes to cloud computing because you're going to have these companies that have, like the server I was talking about earlier, loaded out to the max with RAM, storage space, CPU, right? They're going to be fast computers, beefy computers. But when you order your cloud services, you're not the only one on that physical server, I promise. That's not cost effective. They're going to sell that server, they're going to break it up into little chunks, right? They're going to call it maybe like a VPS, virtual private server. So you can say, yeah, I need a server. So they'll sell you whatever you want to buy. Let's say you buy 8 gigs of RAM, so much storage space, and they promise you so many CPU cycles. This is what you're guaranteed to get. So you got 8 gigs. The person down the road has 8 gigs. The next person has 16. The next person has 16. The next person only has 4. And eventually you have 4 dozen people on this one physical machine. And you don't have any idea who they are, which is fine. I'm not saying the company's doing anything dirty, shady, or malicious. They're making money. And you know that. But jumping out of the hypervisor could be a problem for you. Because if somebody jumps out of the hypervisor, out of their guest operating system and compromises that hypervisor, because the service provider does not have their system secured, they may be able to get to your your guest operating system now, which may be a real problem for you because what you're hosting up there could be sensitive information. So we have to be careful with that kind of stuff when it comes to virtualization. Now, we can also have virtualized networking. All right, so this falls under the software design network. Now, the purpose of a software design network, or an SDN, is to separate traditional network traffic into a few different components: the raw data, how the data is sent, and what purpose the data actually serves for our needs. So we can break them up into the infrastructure layer, or the data plane. This is our network switches and routers and the data itself, as well as the process of moving that data, or forwarding the data, I should say, to the appropriate destination. We have the control layer, or the control plane. You may have heard that before. The intelligence and devices that works in the true middleman fashion. These determine how traffic should flow based on the status of the infrastructure layer, the one we just talked about, where the data, the routers and switches and everything are, and the requirements specified by the application layer, which is going to be the next layer. Now, the application layer, or the application plane, this is our network services, our utilities and applications that interface with the control layer to specify the needs, the requirements, and then that control layer is going to talk to the infrastructure layer. Probably should have turned it the other way around, maybe. Made more sense for you. We have our application layer, down our control layer, out to our infrastructure layer. So it's going out and about when we get to that point. We can also have a virtual SAN, all right, a storage area network. This leads into software-defined storage. Now that is something that VMware actually offers, and it enables enterprises to pool in their storage capabilities. So we can have all of this in one spot. We don't have to necessarily break out our storage capabilities when it comes to those virtual servers that I talked about, those guest operating systems. It's meant to instantly and automatically provision virtual machine storage through simple policies that are driven by the virtual machine that's controlling this virtual SAN. So we have, let's just talk about a SAN just for a second though, a storage area network, right? That is a network that's designed for storage capabilities to support our infrastructure. We could have many file servers out there, redundancy built in, clustering, fault tolerance. We have all of this in our storage area network. High-speed data communications, that mediums we talked about with fiber connections, using different protocols, maybe CISSP, fiber channel over Ethernet. So that's a traditional SAN. We could do the same thing virtualized though, all right? Think of that server I talked about. We could have a virtual SAN in there. We do have a virtual machine running this, but instead of us saying, well, we need this for this virtual machine, I need this for this virtual machine, we take all of our resources, the 10 terabytes of space, and we say, okay, we have 10 terabytes of space in this SAN. Every time a guest operating system needs something, it can automatically, like we said, automatically provision, or let me back up, it will ask for that virtual machine. It'll say, hey, I need some storage. Now that virtual machine running the SAN will say, okay, and it will provision out the data or the space, needed for that guest operating system. That way, that takes the pressure off you as a system admin. You're gonna think, well, I gotta allocate so much here and I gotta allocate so much there. Because if you don't do it dynamically, you may say, okay, I'm gonna allocate 100 gigs for you, I'm gonna allocate a terabyte for you, I'll allocate 10 terabytes for you. Well, they may not need all that space. They may never use it. So don't waste it. Put it in our SAN. Let the software-defined storage take care of that allocation and provisioning for you. And that takes pressure off you as a system admin or network admin or whatever hat you're wearing that day, right?